So we're going to continue with Poisson structures. I'll spend the first few minutes recalling what we did last time. So we started by motivating Poisson structures by talking about the problem of taking a smooth function A on some open subset U of a manifold, I'll say R2 in the diagram on the board here, and rotating that in some way to get a vector field on the level sets of A. And if A was the Hamiltonian of a classical mechanical system, then the vector field we get by rotating that gradient of A on the level sets at every point, that defines a vector field, and the flow, the integral curves of that vector field define the dynamics. So then we discussed the problem of taking that picture in R2 and doing it in higher dimensions. We saw that from that story, solving to find the integral curves, we derived the classical Poisson bracket and the fact that df dt of f was, if f is a quantity defined in a neighborhood of an integral curve for that vector field, then df dt would be given by the Poisson bracket of f with the function used to define the vector field. And that was that story. Okay, so then we started the process of going to higher dimensions. I motivated the sort of formal structure of that problem in terms of the Poisson bracket being a derivation in both variables. So that's what led to talking about bioderivations. So remember, a bioderivation on a K algebra over a field K was a pairing, here curly bracket from S cross S to S, which is a derivation in both variables separately. It's bilinear and it's antisymmetric. And remember, the antisymmetry followed from the fact that we want every function to pair with itself to give 0. And that was because if you fix one of the inputs in our biderivation, so say blank comma A, that's a derivation, and therefore in some sense a vector field, and we want that vector field to be perpendicular to sort of the gradient of A itself. That was the thing we wanted at the beginning, to get a vector field on the level sets of A. So that's what leads to this antisymmetry condition. And so that structure is called a pre-Poisson structure, and then a Poisson structure was where we had in addition the Jacobi identity for this pairing, which is then a Lie algebra. Okay, so we did a bit of the elementary story of how to work with these pre-Poisson structures. This lemma allowed us to notice that given two polynomials, so a pre-Poisson structure on a polynomial ring was determined by how you pair the variables by this formula. That follows from the biderivation property. And more generally, if you have generators of an algebra, the structure is determined by what it does on the generators. The easiest example of a Poisson structure was to rotate some coordinate into another chosen coordinate. So usually you call those Q's and P's for positions and their conjugate momenta. So if you divide the coordinates up into Q's and P's and some Z's which just don't interact with the Poisson structure at all, that is, they pair with everything else to give 0 in the Poisson structure, then you can define this kind of standard Poisson structure. Qi with Pj is delta ij. And then in that case you get this standard formula. And now we're nearly to the end of last time. Right, as I said before, we get a Poisson structure by having the Jacobi identity. And that was where we finished last time. Okay, so I'll outline what I'm going to do this time, but first, are there any questions that people want to ask about last time, or while you're thinking. I'll just check through my notes from last time. I think there was one example I didn't give that I want to start with today. Okay. So I'm going to give this talk in another spot. So I want to start with an example that I didn't give last time of well, it's kind of the example I just showed you, with a Q and a P and two Zs, and just note what that means to have some degrees of freedom that don't couple to anything under the Poisson structure. So remember that the Hamiltonian by itself as a function doesn't generate dynamics on its own, so to speak. We need the Poisson structure to tell us that given degrees of freedom sort of can exchange energy between them. Okay. Just a moment. Right. So, example. So after this example, I'll outline what's going to be on the agenda for today. So consider the function h, which is a half q squared plus a half p squared plus a half z squared, and the Poisson structure where qp pair to give 1. And if I only specify some pairings, then you presume that all the other independent ones are 0. So this implies that ZQ is 0 and ZP is 0. It doesn't imply. My convention is that since I only wrote down this one, those are implicit. And of course, P paired with Q in the other order is -1 by antisymmetry. Okay. Well, on the level set, that's given by h equals a half. Right, so the two sphere. So if this were my Hamiltonian and I used this Poisson structure to give myself a vector field on this level set, well, by the kind of material that we set up last time, the vector field will be this one. Which gives me P ddq minus Q ddp, which of course stands for the ability of the system to decrease the momentum and increase the position, and vice versa. So the picture, if I were to draw this as if I were to draw the sort of implicit potential energy here, which I suppose, I don't know that this picture is really very helpful, but I think it might be a way into it, if you like. If I were to think about this as kinetic plus potential energy, so the potential energy, I mean, it's of course misleading to call it that, but if I were to think about it that way, write v as a half q squared plus a half z squared. Then somehow the fact that I can only exchange energy between q and p and not between z and p, and that comes down to this, or if you like, the fact that this is the vector field that gives the time evolution, means that I could imagine a trajectory like this in phase space, right, which would move backwards and forwards in this direction by exchanging q with p, but you could never go that way, right? You're stuck in this slice of the bowl, so to speak. Okay, so what I want to illustrate with this picture is the connection between these ingredients, right? The Hamiltonian, the fact that the Poisson structure couples q to p. What that means, how that translates to dynamics is the way it appears in the vector field which governs the integral curves. And the third thing I want you to notice is the role of z here. So what is z doing? Well, you could kind of think about it as being parameterizing the ground state energy. It doesn't interact with the dynamics at all. Right? So this is what we're going to call in a moment a Casimir. Which is a function which doesn't couple to anything under the Poisson structure. Okay, so the agenda for today is to talk about, as I promised last time, Poisson structures on quotients of polynomial rings, that is, Poisson varieties. That's a topic that we need to know about in Arakawa and Moreau. To come back to this particular example and define properly what Casimirs are. And then I'm going to talk about Poisson manifolds and the correspondence between what I called pre-Poisson structures last lecture and sections of the second exterior power of the tangent bundle, which hopefully makes the connection for those of you who know about symplectic structures to symplectic structures. And then I'm going to hopefully, if I get there, finish by stating, so we'll talk about the rank of a Poisson structure, which is the only local invariant of such a structure, the relationship between the rank and Hamiltonian paths, and then I'll finish by stating how to derive the symplectic foliation of a Poisson manifold from a collection of Casimirs, which, if I remember correctly, is sort of in the direction of Johanna's question at the beginning. Maybe it was the end, I forget, of last seminar. And that is already in this picture, sort of implicitly somehow. It's the role of Z. The level sets of Z in R3 in this case are what I call the symplectic leaves of the foliation. So that's the role played by Casimirs. Okay, so that's the plan. Any questions before we get into it? All right, so Poisson varieties. We're not really going to spend too much time thinking about varieties for their own sake. Mostly we'll just be talking about Poisson structures on the coordinate rings. So in the following, let K be an algebraically closed field of characteristic 0. Just for convenience, mostly. And let S be the coordinate ring of an affine variety. That is, take a prime ideal and take the quotient. So Z, which is the common vanishing set of all those polynomials, in ANK is an affine variety. I'm still following the same textbook as last time. There's different conventions about whether a variety should be irreducible or not. Just to stick with their terminology, I'll assume so. It doesn't play any role in what I'm going to present, at least today. Okay. So to talk about Poisson structures, sorry, I'm not quite ready for that yet. Yeah, right. So by a pre-Poisson or Poisson structure on Z, we're just going to mean such a structure on S. Okay, well, what does it look like to have a pre-Poisson structure on S? We know a fair bit about that because S, while it's not a polynomial ring, is generated by the xi's, or rather their equivalence classes, and therefore we know that the structure is determined by the pairings of those generators. Right, so by what we said last time, if I take f and g in the polynomial ring, I have so I'm going to use bar to denote the equivalence class in S. Yeah, actually, now that I think about it, there's a little bit of a subtle point here that I'm at the risk of skating over. So maybe let me say this more carefully. I am invoking the result that I mentioned, but let me do it explicitly. So suppose I'm given a pre-Poisson structure on S on the quotient, and let me define a map from S cross S to S by sending a pair F bar G bar to this thing I just wrote. The first question is that well defined? It could fail to be well defined because I'm defining it by choosing representatives of the equivalence classes, right? Yeah, I'm sorry. This point in my notes is sort of not wrong, but also not really the way I think I want to talk about it. Okay, so let me try one more time. So we're going to suppose given a pre-Poisson structure on S, then the following map defines a pre-Poisson structure on the polynomial ring. Okay, by I'll send a pair of polynomials, fg, so I'm going to call this structure curly bracket 0. So fg0 is going to be where these xij's are such that when you take them modulo I, you get the pairing of xi and xj. Right, so we're given a pairing on S. That means this pairing, for the reasons we discussed last time, is determined by how it pairs the generators, the xi's, and those are exactly these pairings. But those pairings are in S. But every element of S, pick a representative of that equivalence class and call it xij. Okay, so you're making these 2n choices. Well, not quite 2n because you want them to satisfy. So I guess you choose them so that xij is equal to minus xji. Right, so you along the diagonal there's 0, and then you choose 1/2 of them, and those determine the others. Okay, so you can choose representatives in the polynomial ring that make this work. And as we discussed last time, any choice of an antisymmetric matrix of polynomials defines a pre-Poisson structure on the polynomial ring. So this is a pre-Poisson structure. So what I'm trying to do is to figure out how to get Poisson structures on the quotient. If I had one, then I could construct this antisymmetric matrix of representatives in the polynomial ring. And what more can I say from that point? So for this pairing 0 to induce a pairing on S, we need at least that so we're sort of thinking about this pairing on the polynomial ring inducing one on the quotient. To do that, you'd have to be able to change either capital F or capital G by an element of I without changing the value of the pairing modulo I. So that would mean what I just wrote, right? That if you were to pair anything, any F, with anything in I, you should get something in I. Right? So I should be something like an ideal. On either side, or both, it's the same, with respect to this pairing. Okay, and since that's a derivation, right, so as soon as you see this as a derivation, you should look at F and think about it as made up of linear combinations of monomials, and just hitting all those monomials with the derivation and reducing this to a question about the variables themselves. So that's if and only if for every xi this works. Or what's by definition the same, we need that this expression here belongs to I. I'm going to call this star. So that's a condition we'd need on, remember the pairing on the polynomial ring is determined by this antisymmetric matrix of xij. So what I'm looking for is a condition on this matrix which ensures that this pairing passes to the quotient. As soon as it passes to the quotient, it's kind of going to be automatic that it agrees with my original pre-Poisson structure. Right? So what condition on the xij's do I have to have? Well, this is one of them. This is a necessary condition. And if you think about it, you can see that this condition is independent of the choice of representatives xij that I chose for those equivalence classes. Okay. So lemma. This is enough. That is, if you have an antisymmetric matrix, with some representatives xij, and star holds for those representatives for any choice of representatives or any particular one, that's the same. We have a pre-Poisson structure on S, defined by take two elements, choose representatives, differentiate the representatives, and then stick them back in the quotient. Now, why is this not just, it's kind of obvious, but why is it not completely obvious? Well, I have to argue that this is a pre-Poisson structure, that it's a biderivation and so on. I also have to check that it's independent of the choice of representative that I choose of f, right? I choose a representative and then I differentiate it. Why is that? When I stick it back in the quotient, why is that not something that depends on the choice that I made? All right, well, that's just due to star. So proof, the right-hand side, which is this by definition, well, that's a skew-symmetric biderivation. That is a pre-Poisson structure. As soon as it is well defined, right? That's the only thing we need to check. But that follows from the fact that if I were to change the representative by an element of I, so then take the pairing 0 and stick it back in the quotient, well, by linearity, that's this, and then by star, that second element is in I. So that's what I started with. Okay. So the right-hand side is in fact independent of the choice of representatives, and then it's easy to see just from its form that it's a skew-symmetric biderivation. And that's it. Right, this is the definition. Okay, so to get a pre-Poisson structure on a quotient, I just have to have this condition star. I mean, in my notes I go through, okay, to get a Poisson structure you need that antisymmetric matrix to further satisfy the Jacobi identity, but that just sort of takes an obvious form. You need to have it hold modulo I, and I'm not sure there's much point writing it out, because we're not going to construct examples right now of such things. Maybe the final remark I'll make on Poisson structures on quotients like this is Perhaps relevant to what we're going to do with Slotowee slices, I don't know. But suppose that you have generators for I. Right? So if I is given by a list of generators, then this condition star, again, using the fact that it's a biderivation, can be reduced to just checking on the generators. So you need j equals 1 to n, xij, dk, I don't know, alpha. And what does this condition say? Well, it says precisely that if you look at that Poisson matrix, right? So remember that the term Poisson matrix refers to this matrix of this antisymmetric matrix of xij's, the structure matrix for the Poisson structure. The xij's make up. So if I take so xi bullet, I mean, this is a dot product, is my point, right? So this condition here says that something is in I. I is exactly the set of all functions that vanish on my affine variety. So this says that xi bullet, which is a row, so i.e. all rows of X are orthogonal to the gradient of K alpha on Z. Okay, so that's a kind of natural condition. I won't dig into it much further now, but you could imagine that meaning something. Okay. Thinking about whether to jump straight into Poisson manifolds, or I was going to talk a little bit about I think I'll go through this stuff. Okay. Any questions so far? Okay, so with the same setup, so let P be in my variety, and let MP be the corresponding maximal ideal. So by the fact that P is in Z, we have that MP contains the ideal I. So throw your mind back to the introduction that I gave to thinking about tangent vectors to affine varieties in terms of K-algebra homomorphisms. By definition, a tangent vector to Z at P is a K-algebra morphism that looks like this. From S, the quotient, to K epsilon, mod epsilon squared. This lemma could have gone in those lectures. I think it's worth doing it now. Why am I talking about tangent vectors to the affine variety? because, well, clearly Poisson structures interact with tangent vectors, right? They're about constructing vector fields on level sets and so on. So if I want to talk about Poisson structures on affine varieties, it's natural to introduce this. And in particular, I needed to talk about the rank. So the way I'm going to introduce the rank of a Poisson structure on an affine variety is by taking the Poisson structure, which is some skew-symmetric biderivation, and from it producing a skew-symmetric bilinear form on the cotangent space at any given point of the affine variety. And to do that, I need to actually talk about the tangent and cotangent space of my affine variety. And that requires upgrading what we discussed some time ago, just a little bit. So bear with me for a moment while I do that.
Sorry, Dan, in the tangent vector, do you want the local ring S at MP?
No.
Or where does P come into it then?
Oh, thank you. Yeah, yes, that's right. Is a K-algebra morphism such that yeah. Yeah, I think it's better to set it up the other way, but I could say it like this, such that so the way it worked, if you recall, is that phi of f is going to be fp plus just thinking about the best way to say this. Yeah, I'll just do it. Is a K-algebra homomorphism such that the composite, for it to be a tangent vector at P, yeah, thanks. Oh no, this wasn't correct. If I post-compose with the map that sends epsilon to 0, this map here, well, that's a K-algebra homomorphism to a field, so it's exactly quotienting out by some maximal ideal, a unique maximal ideal, and that maximal ideal should be MP. And recall, by precomposing with the quotient map, that every such psi is of the form psi equals psi pq. Psi pq of f is f of p plus sum over for some q, they're all of the form psi pq. Okay, so now let me state the lemma. Lemma, there is a bijection between the set of all K-algebra homomorphisms from S K epsilon mod epsilon squared to the disjoint union over all points of this vector space, which is appearing for the first time. Excuse me. Shut up. So remember, I is the defining ideal of my variety. So this is telling you what the space of tangent vectors at any given point is. It's this thing that appears in the disjoint union. And the map sends psi pq to the function that takes a g labeled with the p. Let's not worry about that. So it's what I just wrote out. So we take a tangent vector at p, it's going to land in that component with the p, and it's going to be the linear functional on that quotient, which takes a g, that is something that lives in here, an equivalence class, and maps it to that number. Oh, I guess I missed the epsilon, as I have done before. On the previous board, there's supposed to be an epsilon here. Okay, proof. I'll be quick about this. So let's call this star. I've used star before. Now this is star. I just have to convince you it's well defined, injective and surjective. Map star. Well, let me see. Maybe I'll skip the proof. Let me see how much of it's relevant. Well, at least surjectivity is the part I really want, because that's actually contains somehow the meaning of the mp squared plus I, which I think is the one thing that's not obvious to you, perhaps. Okay, so I'm going to skip well-definedness and injectivity. Skip. I think I forgot to circulate the notes from last time, but I'll send around the notes. For surjectivity, which is what I want you to see, let lambda be on the right-hand side. So that is a linear functional for some p from this guy to k. And let's let qi be what lambda does to the equivalence class of xi minus pi. That's one of the generators of MP. Okay, well then take that p and that q, and I get a psi pq, and that's a k-algebra homomorphism from here to k epsilon mod epsilon squared. And then for, I hope this isn't the, do I have another board here? Yeah. So for f in I and p in the variety, I compute the following. Psi pq of f is fp well, fp is 0. Right? Because f is in I, and I is the ideal of things that vanish. So remember, we're talking about some subvarieties sitting inside an. And we're trying to discuss points and tangent vectors. So f vanishes on z, and p is in z. So that's 0. And now let me substitute what qi is. So qi is, by definition, this. That last thing I just wrote is just a scalar, so I can take it inside the lambda, which is, after all, linear. Okay, but in the Taylor series expansion of f, we have that f is equal to f of p plus the first order term, which is what I just wrote, but not modulo I. Okay, plus higher order terms. What do the higher order terms involve? Well, they're higher order in the sense that they have these kinds of things to some power greater than or equal to 2. Those kinds of things are the generators of MP. So the higher order terms are in MP squared. F itself is in I, and that is 0. So what this shows you is that that expression there lies in MP squared plus I. That's the point of this, this ideal. MP squared plus I is where the first order piece of the Taylor series expansion of an f that vanishes on Z lives. But lambda vanishes on such things by hypothesis. Right? So hence psi pqf is 0, because this being an MP squared plus I means this here is actually 0. Okay, that means that psi pq factors as s k epsilon mod epsilon squared as required, because that's something in the left-hand side of my claimed bijection, and it maps to the thing lambda that I took on the right-hand side. Okay, so that's a little bit more algebraic geometry than we got to last time. Now this allows me to actually define the Zariski tangent space and cotangent space of my affine varieties, which I guess we want to know about anyway. So definition, the k-vector space that's involved there, which we write as TPZ, is the Zariski tangent space. Note the dual, right? So it's a bit confusing because, of course, we also have the cotangent space, but that's the dual. Hopefully the previous lemma makes clear why this is the tangent space, not its dual. To Z at P. And the dual of that, that's a finite dimensional vector space. I guess yeah, okay, that's a good question for the audience. Why is that a finite dimensional vector space? I mean, MP, it's a vector space, but it's infinite dimensional. Why is this quotient finite dimensional? We discussed this last time. That's kind of clearly n-dimensional, spanned by the equivalence classes of the generators of the polynomial ring. What's the relationship between this quotient and the other one? Well, clearly if I mod out by more, I get a surjective map here. So therefore, I get an injective map back the other way. Taking k linear joules over the field. So since this is finite dimensional, the other thing must also be finite dimensional. And what's this map? Well, that's the inclusion of the tangent space, the Zariski tangent space at P to Z, into the tangent space of the ambient affine space. Right? I'm going to use that actually in a moment. So note that this is spanned by the duals of these guys, and we have been trained to write those as ddxi, right? So this is spanned by the ddxi, and therefore TPZ can be thought of as vectors sitting inside that space, which makes sense, they're tangent vectors. Okay, and the Zariski cotangent space is the double dual, or just the thing itself, since it's a finite dimensional vector space. All right. Now for the rank. So I'll just keep all the notation from before. So this is going to be a Poisson structure on an affine variety Z. So the next lemma starts the transition from these Poisson structures to sections of exterior powers of the tangent bundle. So there is a well-defined skew-symmetric bilinear form, not biderivation, bilinear form. I'll write it as pi p, depending on the Poisson structure. Oh, I guess my bad from before, but the Zariski cotangent space, I think I didn't give a name to it, but it's this. How is it defined? Take a pair of cotangent vectors, or what's the same, just elements of MP, modulo that smaller ideal. Pair them. I guess, strictly speaking, I should say something like this, right? Okay, so I should say what this means. So take F and G, their equivalence class, so those are elements of MP. F and G are representatives of elements in the cotangent space as defined on this board. Pick representatives, pair them in S. Yeah, I guess the notations. I think I was a little cavalier about this earlier, but MP is a maximal ideal in the polynomial ring, but I can also think about the induced maximal ideal in S, the quotient, and that's what I mean here. Since I is contained in MP, it doesn't really matter. I could have introduced new notation for this ideal in S, the quotient ring. I didn't think to. So what I really mean by this lemma is pick representatives in S, right? Because MP is viewed as an ideal in S. Apply the Poisson structure, which after all is a map that takes a pair of things in S and gives you something in S. Get an element of S, and then any element of S gives you a well-defined function on the set K, on the set Z. Right, that's the point of the coordinate ring of an affine variety, because if you have any function that vanishes on Z, of course, doesn't change the value So up to elements of the ideal I, you have a well-defined function on Z. So this formula makes sense. Proof. Well, MP squared MP is contained in MP by the biderivation property. What does that show you? Well, it shows you this is well defined, that is independent of the choice of representative, because if you chose a different representative for F here, you would change this thing here by an element of MP squared plus I. Yeah, maybe I should write this out. Since if K is in MP squared plus I, then F plus KG well, the elements of I, I'm working in S, right? So I don't have to worry about elements of I. They're all killed by everything. So that is just F plus K prime with G, which is F with G plus K prime with G. But this is an element of MP squared, and this is an element of MP, and by the biderivation property, this thing here is itself in MP. And anything in MP vanishes at P. That's what it means to be in that ideal. Therefore, F plus Kg as a function at P is the same as F paired with G at P. Which shows that this is well defined, independent of the choices, which is what I claimed. That it's well defined, that it's skew symmetric and bilinear follows from the fact that the pairing is so. Okay, so the point here is that out of a Poisson structure on an affine variety, you can construct a bilinear pairing on the cotangent space at any point. And then I can define the rank. So the rank of the Poisson structure at P is the rank of this pairing. Or if you like, that means the rank of the corresponding linear transformation. I'll call it pi prime P from here to here. We'll talk a bit more about that maybe in a minute. The rank is denoted like this. The rank of that's the rank of the Poisson structure at a point. The rank of the Poisson structure is the maximal rank at any point. Okay. So that's the sort of slick way of introducing the rank, and it gets us to thinking about these skew-symmetric bilinear forms as opposed to biderivations. But from a more practical point of view, maybe it makes sense to think about the rank in terms of the Poisson matrix, right? So if I take the Poisson matrix, which determines the Poisson structure, that's a matrix, skew symmetric. I can just compute its rank, right? The rank at P of the pairing is just the rank of this matrix evaluated at P. Now, the reason that isn't a slam dunk as a definition is that it depends on the choice of these representatives, right? So the Xij depend on, remember Xij was the pairing of Xi with Xj. I'm not bothering with the bars because I'm evaluating it at P in the end, so I don't care. This depends on the generators, right? It depends on how I'm presenting my variety and how I'm embedding it in an ambient affine variety. So it's kind of good form to not take this as the only definition, but to compute its rank. So maybe it's good to explain why these two things are the same. They're not obviously the same, I guess, right? Okay. Now, by definition, the cotangent space is spanned by the equivalence classes of the xi minus the pi's. Right? Why do I care about that? Well, the rank of the bilinear form is the rank of this linear transformation that's related to it under a junction, essentially. And to compute the rank, I need to just take a spanning set for the domain, hit it with the pi prime p, and see what the dimension of that image is. Okay, so the TPZ star is spanned by these guys, which means that so the rank at P of the pairing is the dimension of the space spanned by now for a calculation. Well, the image, as I said, under pi p prime of this as a subspace of TPZ. And here, recall that I'm allowed to think of this as sitting inside TPAN. That's useful because I know a good basis for that. I may not understand much about TPZ necessarily. And what is this? Well, by definition, that's this expression. Pi p of xi minus pi with xj. And then ddxj. Right, so these guys form a basis for here. So this is a set of vectors, and I'm taking its span and asking for the dimension of that. But by definition, pi p of those two guys, that just means, this here is literally just pairing it. It's just notation for the pairing. Pairing with a constant gives you 0, so that's just xi, xj, ddxj, which is, well, evaluated at p, right? Forgot about that. So evaluated at p. But that is the row or column space of xp. Let me have a look. I'm taking the i's. The i's are the rows, so that's the row space. Not that it matters for the rank, but which is the row space of xp. Okay, so the ranks are the same. Okay, so I'll state some basic properties of the rank. Go back to that example, and maybe that's all we'll see what I have time for, but maybe the Poisson manifolds and the main theorem about symplectic leaves will take place next time. That's okay. Okay, proposition. So let's take a Poisson variety. One, the rank at any point is even. Actually, there's some errors in this textbook to do with the following point. They just sort of assume every point is regular, essentially, without saying so. If we have a regular point, that is to say, a point where, so by that I mean the dimension of the Zariski tangent space is equal to the dimension of Z. The dimension of the Zariski tangent space is always greater than or equal to that dimension, but it may be more if it's a singular point. Okay, so assume it's a regular point of Z. You might think, well, aren't we talking about singularities in the end? To be yes, but not these singularities, I think, so as far as I know. So we take a regular point of our Poisson variety, the rank of P there, it's even and it's less than or equal to the dimension of Z, which very well may not be even dimensional, right? So this is kind of an important point. One, well, XP is an anti-symmetric matrix. So its rank is even. You might like to, maybe, I'm not sure if you remember the argument, but that's not difficult to see. And for the second point, well, this is why I was going through this material just now for the last 15 minutes. Because what was the rank? That was by definition, the first definition, the dimension of a linear transformation that looked like this. Right? In particular, it's bounded above by the dimension of the codomain, which by hypothesis is the dimension. Okay, so the rank, so this last point here, if I just talk about the rank of XP, well, XP has as many rows and columns as there are variables, right? It's an n by n matrix. So it's not automatic that I can see from that it's bounded above, its rank is bounded above by the dimension of Z, which of course depends on I, how many things I cut out of that affine space, AN. So it's only clear from the presentation of the rank in terms of this bilinear form connecting the cotangent and tangent space that the rank is bounded above by this. Okay, so this is the important local invariant of a Poisson variety and also of a Poisson manifold. One more definition, and then we'll finish with the example, I think. So if I have a Poisson variety, and the rank is equal to the dimension for all P and Z, we call this a symplectic structure. In particular, the dimension has to be even. So a symplectic structure is just a full rank Poisson structure. I guess this actually implies that it has to be regular, the way I've written the definition, I think. So I don't have to add this as a hypothesis, but I might be a bit cautious about that. All right, back to that example with Q paired with P and the Z floating off on its own. So Z, a bit boring, it's just A3 with coordinates Q, P, Z. Yeah, as I mentioned last time, I was trying to give an interesting example of a Poisson variety, just using the equation for the sphere, but the calculation got away from me a bit. So maybe I'll come back to that sometime. For now, we'll just take the affine variety to be the whole space itself. The pairing is the one I considered before. The point I want to make here is, okay, so the Poisson matrix is just this antisymmetric matrix. So what's the rank? Well, it has rank 2 everywhere. So what does the rank count? Well, the rank's even, and it counts the number of QP pairs multiplied by 2. Right? So that's how you think about the rank. Yeah, let me see. When do we start? 1:15. So we usually go for another 15 minutes from now, right? This is an hour and 15 minutes now, so I think that's right. Okay, so yeah, I'll define Casimirs and maybe make a start on the Poisson manifold material. So I mentioned Casimirs already in the context of this example, right? So let's now make a formal definition. Back to Poisson algebras. Back to general algebras, I guess is what I mean. So let S bracket be a Poisson algebra. Oh yeah, one comment I wanted to make in passing is that, well, what's the role of these antisymmetric matrices? How should you think about these conceptually? Well, that's the point I made at the very beginning, right? You're rotating the gradient of A into its level set. That rotation, these antisymmetric matrices that we have from the Poisson structures, they're of course the infinitesimal generators of rotations. What are those rotations? They're exactly the rotations that swap between Q and P, or which give us this rotation, right? So you can think of the role of the Poisson structure as being really a generalization of this original observation about rotating the gradient. So given a Poisson structure and an element, the derivation, which I'll in a moment explain the precise connection between this and a vector field, but for now it's just derivation. We call the derivations that arise in this way from the Poisson structure a Hamiltonian derivation. And denote by ham S bracket all such derivations. Okay, so the vector space, or the K module of all Hamiltonian derivations is called ham, and we get a map from S to the set of hams, which is H goes to XH. The kernel, i.e. all those functions such that P pairing with H is identically 0 are called Casimirs. I don't actually know the history of this term. Presumably, I first learned this term in connection with like Lie algebras and universal enveloping algebras, but I very much assume that this is the original Casimir. Okay, so in this example, as I mentioned before, Z is a Casimir because it pairs with everything to give 0. Okay, so I'm going to make a start on the theory of Poisson manifolds, which is very similar to what we've been doing with Poisson algebras. In fact, the definition will say that a Poisson manifold is a bivector field that induces a Poisson algebra structure locally. But so I guess the following is a fair bit of just like terminological stuff, but there really is some content in the relationship between skew-symmetric biderivations and elements of the second exterior power. I guess that's the main thing that probably bears explaining closely. All right, first some definitions. Everything I'm going to say works for complex manifolds, but I'll just stick with smooth manifolds over R, I guess, for simplicity. I'm going to write OM for the sheaf of smooth functions. And OMP for germs of smooth functions. So that's pairs consisting of open neighborhoods. I guess U should contain P and U should be open. Modulo the usual relation. I'm sort of assuming you know about that. For the R algebra of germs. So we write FP or F for the equivalence class of that pair in the ring of germs. All right, so a bilinear map, R bilinear, BP, which takes a pair of germs at P and produces a number, is I'm just going to call it a biderivation. The textbook says pointwise biderivation, but I think that's a bit redundant. It's almost the same condition we talked about earlier, except remember the Poisson structure lands not in real numbers, but in functions. So, well, if we're all F, G, and H in the ring of germs, BP, F, G, H is FP, BP, G, H plus GP. And similarly in the other variable. FH FG. I won't write it out, but it's clear what it means for such a bilinear map to be antisymmetric. Okay, so now for some content, the relationship that I mentioned, lemma. Let me see, how many boards do I have? Actually, just bear with me. I'm going to move. This board doesn't. I probably need a few more boards. Any questions while I'm running? Okay, lemma. There is a bijection between the second exterior power of the tangent space at P and these skew symmetric biderivations as above. Here I've switched, I'm in the manifold setting, right? So TPM is now defined as usual in that setting, and it's not the Zariski tangent space, although obviously they're computing the same thing in the end. And this map sends a wedge product of two tangent vectors to the following skew symmetric biderivation, which takes a pair of germs and computes the determinant of this. So just some terminology. So delta it's a tangent vector. I can apply a tangent vector to the germ of a function and get a real number, right? So this is a matrix of real numbers, and I compute its determinant, and that's what I send this pair of germs to. And that map is my, so I claim, skew symmetric biderivation. Okay. What I'm going to do is just give the construction of this map. And the way it's constructed, obviously you can construct the inverse. So the proof is kind of easy once I construct this properly for you. So that's what I'll do. All right. And the ingredients here are sort of what you need to know to get yourself into the right headspace to understand Poisson manifolds. So let's start with the germ of a smooth real valued function at P. Well, let me say it like this. I'm going to construct this way. So I'm going to suppose given a skew symmetric biderivation. So given BP, we consider for any germ well, we can fix the second variable in BP. That's a derivation. A derivation from the ring of germs to R is by definition a tangent vector. So that's a vector in TPM. So what I've defined for you is a map from OMP to TPM, which sends F to BP blank F. Well, this is a linear map because BP is bilinear, and the joule, the R linear joule, is what? Well, it goes from TPM star to OMP star, and it sends an eta here to the composite of the previous map OMP to TPM via eta to R. Well, sitting inside R linear functionals on OMP are the derivations. Right, which is the tangent space. And I claim that this map, which is the dual of this map, which I've defined for you, factors through that subspace of derivations. Why? Since eta maps to the function which sends g to eta of bp of blank g. That is what it is by definition. So why is that a derivation if I plug in, in the blank? Why is it a derivation in G, which is a derivation in G? Because BP is a biderivation. Okay, so what have I constructed for you now? Well, I've constructed, so we have a map from TPM star to TPM, just like we had earlier, right? But now in the manifold setting, where things are set up slightly differently. And that sends eta, a functional, to what I said. G maps to eta of BP blank G. That's a linear map, which is adjoint to the bilinear pairing TPM star cross TPM star goes to R, which sends eta comma tau to tau of G maps to eta of BP blank G. If you're wondering about what this BP blank G is, well, what does eta eat? Eta eats tangent vectors, right? Tangent vectors are derivations. So this BP blank G is a derivation of functions. That is, it's a tangent vector. Okay. So this is anti-symmetric. Since BP is, and hence factors through the universal antisymmetric map. Which is the wedge product. So factors as TPM star so this is the map I just defined for you that must factor through the canonical, the universal rather, antisymmetric bilinear map, which is the map to the wedge product. Okay, now you need to recall a little bit of linear algebra. Recall the canonical non-degenerate bilinear pairing. Between, so for a vector space V, between the nth wedge product of V and the nth wedge product of V star. There's a non-degenerate pairing which works as follows. It takes a wedge product of n forms, nu 1 through nu n, a wedge product, a wedge product of n vectors, v x1 through xn, makes a matrix out of them, and takes the determinant. So evaluate all the forms on all the vectors, and then take the determinant. Now, since that's a non-degenerate pairing, that's where the isomorphism between the wedge product of V star and the dual of the wedge product of V comes from. It's the adjoint of this map. Okay. So we have that the second exterior power of TPM star is, why am I talking about that? Well, because alpha lives there. Okay, so let me step back a bit. So this blue dagger I constructed from BP, right? I presumed I had this pointwise skew-symmetric biderivation, and I've constructed from that dagger. Dagger factors through the wedge product via a linear map alpha. Alpha lives, well, it's by definition something that lives in the dual of the wedge product of TPM star with itself. And by what I just reminded you of, I can take that dual inside and get the double dual. That's finite dimensional, so that's canonically isomorphic to the second wedge product of TPM. Okay, so alpha came from dagger, and dagger came from BP, and then I can send alpha over here and get my my desired element of the second exterior power, and this combined map here is the desired construction in the statement of the lemma, which, if I go back for you in a moment, right? I claimed I was going to take you from BP to get a vector in this here, and that's the vector I've just constructed by going from BP to that map dagger to alpha and then onto this canonical isomorphism. So maybe I should call this something capital psi of BP. And then we'll go back and call this thing here psi. Okay, next time we'll actually, maybe that's a bit abstract, next time I'll tell you about how to compute that. It's not complicated. Basically, this expression should look familiar from the description of the Poisson bracket, right? It has this kind of determinant feel to it, where you're taking a determinant of a differential operator with a pair of functions. So hopefully that's kind of seems plausible. And if you chase through the construction, I hope you believe that the formula is exactly what I wrote here. That somehow follows from this. Okay, so that's the construction in one direction. But the way I've set everything up, you can see how you reverse it, right? Start with a vector here, go backwards along these isomorphisms, get an alpha, post-compose with the canonical map to get this map, and then just undo all these steps and you'll get back to a skew-symmetric biderivation BP. And then you just check those maps are mutually inverse, as they are by construction, and hence you have this bijection. All right, so that's the bridge between the kind of differential geometric point of view on a Poisson structure, which is often defined as a smooth section of the second exterior power of the tangent bundle. Well, it's a pre-Poisson structure, if you like, that doesn't have the Jacobi condition in it, but and the point of view we've adopted where it's a kind of pairing. And I'll stop there and we'll finish off the rest of what I want to say next time, unless we want to take a break and do something else, but that's up to you. Thanks everyone. Questions?